Numbers have a beauty, a majestic, austere, and ruthless beauty, unbounded in significance and consequence. They're the quintessence of pure thought, a bliss-imbued cavalcade of
Good scene, isn't it? One man crazy, three very sane spectators.
Assuming very sane is not an insult, our very sane spectators are the continued fraction, the set of fractions, and the Pienary expansion. We note the operators for the integer and fractional part of x behave as projections under composition, encapsulate modular arithmetic, like hanging around home, and socialise thus. We extend a natural decomposition by inverting the fractional part, extracting the integer, and inverting and continuing on that way to construct the continued fraction. The important point for us about continued fractions is that under sublinear scaling, the number behaves like a multiple of the continued fraction convergence because of the quadratic convergence of the continued fraction. We note the recursive construction, definition of the convergence, the oscillating convergence pattern, and the relationship with the Euclidean algorithm for continued fractions. We note for beta rational, the set n beta is just the set k over d, k equals 0 to d minus 1. When beta is an irrational number, we use the continued fraction expansion, apply linear scaling, utilise the quadratic convergence to establish the fact that n beta is in fact dense in 0, 1. Beta n approaches beta quickly enough, then the set of limit points n beta n shows the same behaviour. Recall that each number in 0, 1 has a Pienary expansion. We note that P to the S alpha is irrational if and only if alpha is. These facts combine to give us the grid theorem, which states that every revenue class, like P to the S, is covered by infinitely many n. Consider it to be a toy version of commutative algebra, where we are converting questions of irrationality to questions about the solutions of congruences. For instance, corollary G2, A over B rational, X irrational, we obtain solutions to each of those congruences. Corollary G3, alpha is rational, if and only if each of those terms vanish. Corollary 4, P prime, P to the n alpha, dense, if and only if alpha is irrational. Corollary G5, square root of P to the n is dense. Very nice. Here we look at the residue class frequency for the number E and the prime 193. Note the dampened periodic behaviour. Strange behaviour also at the prime 71 for pi and 257
You've got
for
to
gamma.
convince me that you know what this is all about, that you aren't just fiddling around hoping it'll all come out right in the end.
Good point, Sam. Right, what have we got? Beta is rational if and only if it has an infinite continued fraction. We note the sublinear scaling with the quadratic convergence combined to give us theorem 3 density, and theorem 4 converts our questions of irrationality into questions in modular arithmetic.
I'm sitting on top of the world. I'm rolling along.
Notwithstanding the multitude of expressions for gamma, we require only Euler's original definition and focus on the fractional part of n gamma. To learn more about the fractional part of gamma, we ask, when is hn closer to an integer? Precisely when n equals the big part of e to the k minus gamma. Or details in Havel's excellent book, Bloody Ripper, Julian. Now here's our two good buddies looking very dapper. More evocative than useful though, what we need is an arithmetic vibration.
Everything seems lovely when you start to roll.
A primal continued fraction is one where every denominator is a prime number. Here we see the construction by the Dirichlet map of the equivalent of the Fibonacci sequence. In white, the prime continued fractions. D has interesting properties, co-complementary, has measure 0, provides us with our required vibration, and of course the isomorphism between 0, 1 and D, quite amazing. We let beta be in D infinity, alpha an arbitrary irrational number. We define daughter I as shown to obtain the co-prime pairs. We are then able to solve each of the simultaneous congruences by the Chinese remainder theorem while maintaining the convergence behaviour. This leads to the primal continued fraction theorem. we have beta and d infinity, alpha irrational. If for all I we can find solutions to the simultaneous congruences, then beta minus alpha is irrational. We say Fn is contiguously dense in naught 1 if the inverse image of every neighbourhood contains a contiguous set of length k for arbitrary k. What I call the contiguous density theorem. If Fn is contiguously dense in naught 1, then Nfn is dense in naught 1. For the proof, we use the same technique as in the original density theorem. Say we obtain the additional term mu. Mu is irrational, and we have contiguous density. And we note quite happily that the scaled components for gamma and c are all dense in naught 1. I think this was my 9th attempt.
When you're slapped, you'll take it and like it.
The irrationality theorem. Let h and l be two contiguously dense functions on the integers, such that h is rational, l is irrational. Their difference tends to a limit, and does so at a reasonable pace. The proof uses primal continued fractions contiguous density corollary G2 to show a set of fractions n theta is dense in naught 1. Of course, the point of the irrationality theorem is these two corollaries. Euler-Mascheroni constant is irrational, Merten's constant is irrational.